Hi everyone, my name is Guillaume. I work for AstraZeneca in Sweden, and I'm very happy to be here today. I'm going to be chairing the machine learning session, and we've got three great talks lined up. The first talk is going to be from Bernardo Lares and Igor Skokan. They both work for Meta. So Meta was formerly known as Facebook. To introduce them, Bernardo is a Venezuelan mechanical engineer. He works at Meta's marketing science team, and he's passionate about measurement, automation, and R stats. So I can already see we've got a lot in common. And he is also a strong supporter of open source empowerment and democratization. Now, when it comes to Igor, he is part of the global marketing science team at Meta, and he's based in London. He's a nuclear scientist and mathematician by education. And in his current role, he focuses on the intersection of different facets of marketing effectiveness, from contemporary marketing mix model, holistic attribution, experimentation, media insights, and open source. So they are going to be giving a joint presentation, and they are going to be talking about Robin, which is a continuous and semi-automated marketing mix model from the Meta marketing science team. So Igor and Bernardo, the floor is yours. Have fun.
Thanks a lot, Guillem. Let me share my screen. All right, so I think, can you see my screen, right?
Yeah.
Okay, well, thanks a lot for this space. We're really excited to be in the user conference this year. As Guillem just mentioned, our names are Bernardo Lares and Igor Skokan. We both are marketing science partners. We work in Meta, and we're really happy to share today with you what we've been working for like the last 2 years to democratize marketing mix models.
So I will start with giving a little bit of the background to what's been happening and why marketing mix models yet again rise to popularity. So as you probably know, many of you working in data science, marketing science, the data availability is changing with the advertising system rapidly evolving toward privacy. State and regional governments, as well as technology companies, are driving substantial changes on this front. Overall, giving more power to the users is obviously the right thing to do. But what it means that in the just last 3 years, we have seen significant regulations put in place. GDPR in the European Union, LGPD in Brazil, CCPA in California, just to name a few of the main ones. Cookies have also been slowly limited by web browsers, and then this is expected to continue going forward. And then, currently the industry is working through the challenges imposed by iOS 14 in Apple and so on. So really, the advertising ecosystem is changing, and with that, we can see that there are some changes impacting business ability to reach and with businesses with relevant and timely ads. This is on the next slide. And then there is many other things that businesses are now finding harder to do. One of which, and this is the point number 4 here, is more difficult than it was before to accurately measure and report campaign results. Now, the impact of these advertising ecosystem changes on measurement tool and techniques isn't universal. So as an industry was evolving over time, there has been some of the solutions that have been designed around now deprecated mechanisms like cookies or mobile identifiers, for example, multi-data attribution, are much more impacted than on the left-hand side with less impact or less impacted. We have methods like marketing mix modeling, or often referred to as econometrics in Europe, or geo-experimentation. So these rely on aggregated data. Some of it obviously predates the internet even, so doesn't actually inherit any of the challenges. Now, in the hands of the data science community and the modern data scientists, these methods are now being sort of redeveloped and brought again to its digital future. So marketing mix modeling, just to kind of level set, what do we mean by it? It's a privacy-friendly, data-driven statistical analysis based on regression models that has some very strong advantages, such as it allows us to model historical data and understand the effect of marketing and non-marketing activities. So it's kind of unique in that sense as well. Allows us to understand like a holistic business impact. There's no requirement for any of the log level or PII. Everything is aggregated. Everything is aggregated. So there is no need for that. It's highly scalable. It's remarkably customizable. It works pretty much for all circumstances, all businesses, and any metric pretty much can be modeled. And there is innovation, and we're gonna speak about this. Most of our presentation is about how can we make it faster, more accurate, and less biased. So the way how it works basically seeks to understand the aggregate impact of the different drivers, both in the sort of base, like price, category, trends, etc., and the media factors. This is done by assessing multi-correlation between these trends and activities and the KPI, and then from here we can assess the ROI or ROAS, return on investment, return on ad spend across all media channels. Gives us all kinds of outputs, split media, non-media, online. You can drill into great depth of it. So it's very useful for tactical and strategic decisions as well. Now, historically, as you can imagine from the formula, historically this was done manually. Analysts were running these regressions by hand, and it was a lot of craft and a lot of human input and human bias. We believe that this can be changed, and this actually presents itself as an opportunity. And our vision for contemporary MMM is to bring it to its digital future as a machine learning supported, granular, automated, and an experiment calibrated analysis. So basically taking the best bits of classic MMM and the best bits of the classic attribution and come up with a more contemporary view on how this can be done. And this sort of quite lengthy background is why we actually created Project Robin. And Project Robin in a way, and Bernardo's gonna talk about this, is a actualization of this vision, or at least a step towards actualization of this vision of contemporary MMM. And we want to take the whole industry with us. We don't want to build it up ourselves, so we made it as an open source. And over to you, Bernardo.
Thanks, Iggy. To have a better understanding of what is motivating us to promote and develop this project, I'd like to first check what is our vision, what's our goal in marketing science team, and finally, what is Robin. So the vision of this project is to build a community of MMM experts to be able to discuss and contribute in a transparent and robust marketing measurement methodology, open to advertisers from all over the world, no matter their budgets or sizes. The objective of our team at Marketing Science is to help businesses grow based on good practices using data science and privacy. And lastly, very summarized, Robin is an R open sourced package developed by us to facilitate marketing mix modeling in a semi-automated way, leveraging modern techniques to mitigate biases as much as possible. Robin has several benefits that make it quite different from classic or traditional MMMs. For example, traditional MMMs models are run manually by experts that on this matter, and therefore they are very slow processes, and naturally they are much more expensive and exclusive to large advertisers. Another clear example of these differences is being able to have, for example, one model per year versus being able to refresh your model as often as needed with new data that you have available and gain more actionable results as you see fit. In classic models, providers usually set the same ad hoc transformation parameters for all media channels, which doesn't make much sense because every channel has a very different behavior for each advertiser, carry-on effect, and impact on each of our metrics. So with Robin, we optimize these values per media channel to minimize the overall errors, and we simulate these curves that better fit the reality. Also, classic models are often overfitted, which means that they have a very good stats metrics on the model data, but not when applied to reality. And with Robin, we run a rich regression and regularization to select which are the relevant variables, and we reduce overfitting and bias of both the analyst and the model. We also take leverage of Prophet, which is another open source package developed by Meta, to break down trends and seasonalities to enrich our data in an automated way and help the model have a better fit. And finally, and one of the most valuable steps we are pushing the industry towards is calibration. We use the results of incrementality experiments like brand lift, conversion lift, geo lift, or any other lift methodology to pull the model as closer to reality as possible. So not only are MMMs validated with statistical metrics, but we also get as close as possible to the absolute truth, which has been measured with causal experiments. So even though we don't have enough time to break down the whole flow and core features today with you, which we'd love to, we'd like to show that we have a bunch of techniques and open source algorithms already integrated into Robin to help users take less biased decisions across all the pipelines, since Robin ingest the data until we interpret the results and suggest new optimized budget allocations. So feel free to approach us later or bring any of these potentially interesting points to our Q&A at the end, please. So today we'd like to focus on 4 specific pillars that mitigate bias in the MMM training, model selection, and decision-making processes that are already implemented into Robin using these modern techniques we've been talking about. Minimizing human bias is one of the main goals and key challenges Robin helps solve while training these marketing mix models. So as we mentioned, classic MMMs rely heavily on the experience of the analyst when taking decisions in the process of assigning the correct values to transform the variables and the carryover effects, and picking which models are good enough to be considered. So what techniques does Robin currently have to help the user automate and unbias these decisions? So first, using an automated multi-objective hyperparameter optimization with an evolutionary algorithm allows us to effectively sample thousands of possible ad stock and saturation curves and values while minimizing the 3 errors we optimize towards. So the model error, the decomposition distance, and the calibration error if we provide experimental values. Then we have the Pareto Front Optimal Results algorithm, which identifies from all the trained models which we have run the trials and iterations, which of them are closer to the origin, which matches those who have lower errors. That way we can automatically discard thousands of not so useful models before we proceed with the model selection process. This chart displayed on the right shows the performance of the multi-objective optimization. We use Nevergrad, which is another open source package developed in Python. We enable it with Reticulate, and we run at 10,000 iterations in this example using the dummy data set we have in the library. So the axis represents the 2 objective functions to be minimized when the calibration is not provided. And as the number of iterations increase, we can clearly observe a trend to the lower left corner of the plot. This is proof that Nevergrad's ability to drive the model results toward the desired direction in an evolutionary way. And the red lines shown are the first to third Pareto front, which contains the best possible models results for all iterations. So we also use Prophet seasonality decomposition, which uses this machine library for to automatically decompose the trend and seasonality information and include them as additional features to the original dataset. That way we can help the algorithm have a better fit. And we also run rich regressions with Lambda as a hyperparameter. This is a regularization technique that I guess you are all familiar with it, but it helps us deal with intercorrelated explanatory variables in our dataset and penalizes variables given their multicollinearity. So these steps prevents overfitting and allows more freedom when choosing the variables to train our models with. And we use Lambda as a hyperparameter to minimize the bias in the selection of this variable as well. And to the right, we see this dummy chart displayed that shows Prophet's automatic decomposition of our input dataset based on seasonality and local countries event data that Prophet has already integrated. So we just have to tell in which country we are modeling, and the rest is Prophet's work. There's also a lot of bias when picking the right model, which absolutely affects the final outcomes. To minimize this effect, because we can't absolutely get rid of it, we use multi-objective optimization convergence criteria to ensure that there are no further solutions or models that will provide better results, given that the errors are not diminishing while we keep iterating. This means that the optimization algorithm has found the best solutions, and there's no need to keep iterating. And we have our Pareto. Once we have the Pareto front models, we run k-means clustering to be able to once again reduce the amount of useful models to pick from. So with this technique, we are able to choose from the most different models with the lowest combined error for the rest. This way, we can avoid the time-consuming step of comparing very similar models. And we also automate the process of picking the number of clusters to consider using the sum of square within clusters convergence criteria. The last benefit on using Robin to minimize bias I'd like to mention today is calibration. This technique helps us improve the model's predictions using causation data instead of pure correlations. That's the main difference. We strongly believe that integrating experimental results into our marketing mix models is the best choice for model selection. Experiments such as randomized controlled trials are causal by nature and can be seen as the ground truth impact of our treatments. So what we do when providing calibration data is that we minimize the mean absolute percent error, or MAPE metric, between our predictions and our ground truth results. This is a third optimizable objective we add to the algorithm, to Nevergrad, to minimize the errors. And to ensure closer model results to the experiments, we apply a stronger weight to this error by discarding very off results. So now that we've finished running Robin with our data, we have a list of outputs that will help you take actionables. One of the main outcomes you'll find is this one-sheeter or dashboard on the right with several charts per model. So let's see some of the information we can gather from this in order left to right and top to bottom. So the first plot we have is the waterfall chart with a total decomposition of all the independent variables and their dimensions. This provides an idea on the weight of each variable over your modeled independent metric, which usually is conversions or spend. The predicted versus actual plot visualize the time series fit compared with the model prediction. We also have the R squared in the top as a subtitle. So the closer it is to 1, the closer the predictions are to the actual values. we have the media decomposition chart that shows the media share of spend versus the share of effect of ROAS or CPA, depending on your independent variable. This plot also gives us a hint on the intuition of the objective function that minimizes the decomposition distance to avoid extreme cases. Then we have these saturation curves, which show the Hill functions with induced saturation curves for each of these media variables. We have the average media decay rate comparison plot. So this, when using the geometric addstock, it will show you the hyperparameter that was selected. And when using Weibull, which is another methodology for addstocks, it has two parameters, so that change the decay rate over time. So we visualize a distribution of the timings. And finally, we have the fitted versus residuals to visualize the model diagnostic given the residuals and trend, which will also help you detect outliers and possible biases. And of course, in the top section of these one-pagers, we have the IDs of our models, and we have the 2 or 3 errors we optimize towards. So you have these metrics. And before we start closing, I'd also like to mention we enabled additional actionable decision-making information based on a specific scenario you'd like to test, either maximum historical response case for any date range as business as usual, or maximum response given an expected spend. So for the budget allocator, we use a nonlinear solver that allows equal and unequal budget constraints to help us define optimal budget allocation for upcoming cycles. And the diminishing returns and addstock curves, the model prints for us will help us understand the inflection points and locate the sweet spot for our investments on each channel. So we can understand how the more we spend, which will be the expected response. So Robin is an ever-changing and evolving open source package. So as you might expect, we have a lot of things in our pipeline. We have a Python wrapper to enable Python users to run the latest Robin versions using their Python and pipeline implementations. We have nested modeling to be able to have different levels of aggregation and more detailed insights and actionables. We are working on a forecasting or prediction to run future scenarios and simulations. We have to work on a time series validation to avoid overfitting on these forecasts. And there's a Shiny app for interactive usage that will be quite educational and easy to use for non-coders. So we're really happy to be here to invite you all to be part of this community, maybe as intellectual curious people or actively. Since about a month ago, you can install Robin using Cran's repository as our latest stable version, or use GitHub's version to run and test our developing or any other dev versions. You can also, I invite you all to go to Robin's website. In there, you'll find step-by-step guides. We have a dummy data set so you can test it out. We have more details about these features and core advantages, and some public success stories of actual advertisers who have been using Robin to take important budget allocation decisions. So back to you, Iggy.
Yeah, in the last few minutes, I wanted to, in the remainder of time, I want to talk about some of the real business cases. So we have a few. I'm gonna kind of whiz through them because I think we are almost on time. So Resident is an Israeli e-com company, digitally native goods such as Nectar and DreamCloud. They were able to build usable MMM models in just 5 days versus trying for like 5 months before, using their using some other methods, and save 20% in the process. The other cases we have is also about speed. Wittichen is a Polish brand, also was able to save and build very fast models. So yeah, maybe we'll just go. I think we are on time. We have plenty. It's been a ride. There is a lot of companies have found great use for it. So we, as Bernardo was saying, let's connect, let's find, join our community, join our Facebook group or GitHub, find us on LinkedIn or Facebook, and please reach out with this. And thank you so much for having us today.
Yeah, thank you very much, Igor and Bernardo, for this great presentation. I think it was really nice. So for the sake of time, I propose that you answer the questions in the Q&A directly in the chat. And if we've got some time left at the end of the session, let's see if there is some extra questions, if that's okay for you. Cool. Yeah, thank you very much. That's really nice, really great insight about your work at Meta. So our next speaker is Niklas Koenen. Niklas studied a PhD position at the Amy Noether Junior Research Group, headed by Marvin Wright. And Marvin is actually our third speaker today. And so Marvin and Niklas work at the Leibniz Institute for Prevention Research and Epidemiology in Bremen. And today, Niklas is going to be talking about interpreting deep neural networks with an R package, which is called Insight. So Niklas, the floor is yours. Enjoy your presentation.
Thank you very much for the kind introduction. And now I share my screen. So I think now I can see it. Yeah.
That's perfect. Thank you.
Perfect. So welcome to my presentation on how to interpret deep neural networks with the R package Insight. So, and as already mentioned, my name is Niklas Koenen. I'm a PhD student. This is part of my PhD project, and Marvin Wright is my supervisor. He will give the next talk, and yeah, hopefully you will learn something. And so let's start simple. I think many of you have already encountered the following situation or problem. You evaluate your perfectly fitted neural network on a new data point and obtain a prediction. Now you can ask yourself, why did the network make this decision? What were the crucial features in the data to make the network choose this specific prediction? So maybe it's an unexpected or counterintuitive outcome, or you just want to understand it better. So this is the fundamental question in my talk today, and I want to give you a tool, namely Insight, to be able to answer this question on your own with your data and your model. So first, I would like to place our focus today within the large world of interpretability methods, because there are a lot of interpretability methods out there. And first of all, we restrict ourselves to so-called post-hoc methods, which require an already trained model on a regression or classification task. So we are in the classical supervised learning setting. Then there are mainly two big distinctions. The first distinction is between model agnostic and model specific methods. Methods can be applied to an arbitrary model, and model specific methods can only be applied to a specific model class. For example, only random forest or only neural networks, because we need internals for this method. And the next big distinction is between global and local explanations. So global explanations explain the entire model, explain individual predictions. For example, you have an image and you make a prediction of this specific image, and then you have a local explanation. So maybe you have already heard of some of these. For example, Lime and Shapiro values or permutation feature importance are quite famous. However, our focus lies today on so-called feature attribution methods. So we are on the model setting with neural networks. But first, now I want to explain feature attribution methods for neural networks. So in doing so, I first explain feature attribution in general, and then I will give you a brief overview of the most popular methods. So let's start. So in general, feature attribution methods consist out of two steps. In the first step, this is the normal forward pass. You already know from the normal neural network. We have some kind of input data like the sweet cat, for example, or tabular data. We feed it in our neural network, our black box model we want to explain, and obtain a prediction. If we have multiple outputs, we choose a particular output we want to explain. For example, the class with class label cat for the image of a cat. It could also be a dog if we have enough class labels for it. Then comes the second step, the backward pass. In this step, a feature attribution method is applied from the chosen output back to the input. So we go the layer in reverse order back to the input. This means we assign an attribution value to each input feature, which is also known as contribution score or relevance value. These values can be either positive or negative, and they generally describe the relevance or effect of a particular to the selected prediction. For example, in this image, we have blue areas, and blue areas means, or blue pixels means that they have a negative effect to the output prediction, and red ones mean that they have a positive effect, and white means they don't have any kind of effect to the output prediction. So one of the biggest advantages of feature attribution method is that they are extremely efficient and fast. So on the one hand, they can be implemented in already very efficient deep learning libraries like PyTorch, Keras, or TensorFlow. This is it because it's not, of course, we can apply model agnostic approaches to neural networks, but it's too time consuming for neural networks because the prediction process is too time consuming. And in general, only one forward and then one backward pass is required. So we do not need any kind of optimization or estimation procedures, which is normally the case for our model agnostic approaches. In addition, it's input dimension because the number of network evaluations does not depend on the number of input features, which is also the case for a lot of model agnostic approaches like Shapley values or permutation feature importance. Okay, now I would like to briefly introduce you to the most popular methods. I think the oldest and also the very famous one is the saliency map, or also known as vanilla gradient. In this method, we simply calculate the gradient of our chosen output with respect to the input. And this gradient indicates the local rate of change and therefore indicates those features that can be perturbed the least in order to change the outcome the most. In both ways, positive and negative, but it's only valid on a small scale. One extension of this approach is called gradient times input. So we simply take the gradient and multiply by its input. And this is why it's so named. And mathematically, this represents an almost feature-wise decomposition of the output by a first-order Taylor approximation at 0. Another approach, which is gradient-based, is called smooth grad. So it simply takes the average gradient of small perturbed inputs. So we add some Gaussian noise, for example, we calculate the gradient, and then we take the average of all the gradients. Okay, and now we come to the first backpropagation-based approach. I would say the most famous one is called the layer-wise relevance propagation, in short LRP. And the overall goal of the LRP method is to decompose the output into feature-wise relevances. And it works as follows. So in the forward pass, we save our pre-activations. These are the values after the linear multiplication in the hidden layer, but before we apply our nonlinearity. And the individual summands are called local pre-activations. Then in the backward pass, we start by defining the output relevance as the output of our model, because in the end, we want to decompose this one. Then in the hidden layer, we redistribute the upper layer relevance to the lower layers by so-called relevance messages via a specific rule. There are a lot of rules available, and here I want to explain the original one, also known as Z rule. And it's simply the ratio between this one divided by the global pre-activation. And then we can calculate the lower layer relevance by the sum of all incoming relevance messages from the upper layer. So for example, in this case, PRR relevance. And note, we just take all incoming relevance messages like this one and all the intermediate ones. And then we continue this procedure up to the input layer where we obtain relevances for each input feature. One extension for this approach is called, there are different rules, as I said, and the most famous one is the set rule I presented before, the epsilon rule and alpha beta rule. And in the alpha beta rule, there's also the deep Taylor decomposition included, which is also quite famous in the LRP setting. One extension for this is called deep lift or deep lift features. It additionally compares the attribution values with respect to a reference input, x tilde. Hence, deep lift outputs relative effects of an input compared to the reference input. And as you can see, we have an exact decomposition of the difference from the reference output into feature-wise relevances. And the rules for propagating through activation functions, namely rescale and reveal cancel rule, and both ensure that we have an exact decomposition of the output relevances. This is a short note, this is not the case for LRP because the bias term absorbs some kind of relevance. Okay, now we come to our RPack. We make use of the entire efficiency of the torch package, which is built directly on the C++ variant of PyTorch, which is also known as libtorch. So we do not need any kind of Python dependency. But now I just want to answer the question, why inside? Yes, of course, there are already extensive packages for feature attribution methods of neural networks in Python. So namely investigate, deeplift, captum, or zenith. But now comes the problem. All of them are Python exclusive. And all of them work only on specific deep learning libraries, for example, PyTorch or Keras and TensorFlow. So for example, for Zenith, you can only use PyTorch models and not Keras models. And other way around, for Investigate, you can only use Keras models, but no PyTorch model. In addition, some even run only on outdated versions of Keras, TensorFlow, and Python. For example, Investigate and Deeplift only work with TensorFlow 1, but the current version is TensorFlow 2. They only work on older Python versions, Python 2.6 and lower. And all of these methods do not provide any kind of visualization tools, so you have to implement your own plot function. This is left to the user. And now we come inside. So we are the first package for feature attribution methods for neural. And we are a so-called deep learning library agnostic approach. So it can be used with feature models from different packages like Keras, Torch, Neural Net. It's even possible to implement your custom model as a list, and then you can put it in our package. We have no Python dependency, so we use the Torch package, and Torch uses C++. So needs reticulate, for example. And it's easy to use, so you can generate a plot in only 3 steps. And we have various visualization methods for the results, including some interactive plots with Plotly. Now I want to explain to you how Insight works and how to generate an explanation in only 3 steps. To start, we need to install the package, obviously, and we need to create a model. So we are already in CRAN with our first version, so you can just install .packages to install our package. Then you need to create a model. This could be a sequential Torch model or a sequential Keras model, a neural net model, or as I said, you can define a custom model as a list. There are some restrictions, but you can do it by yourself if you want. Yeah. Then follows the first step. So in the first step, Insight converts the given model into a Torch model. This can be done by creating a converter class. It's an S6 class with the trained model as an argument, as you can see here. So we take the model, convert it as a list, and then we convert the list as a Torch model to a Torch model. And you can also set some input names and output names for the labels for the plot and boxplot function we will see later. Yeah, it's also, see, we can access to the model, to the Torch model with the field model. And here, for example, we have 2 layers, 2 dense layers. The first one with the hyperbolic TimeGain as an activation function. And the second layer has a sigmoid function as an activation function. Okay, Then follows the second step, where we apply our method. We use the computational power of the Torch package and apply a selected method to the data by creating an instance of the respective S6 class. And there, for each for LRP, we have LRP create a new instance. We use our converter, the data, and depending on our method, we use some argument name or times input for the gradient method and so on. Then we have a nice progress bar to see the progress. Yes, and after it, you can get the results with the R6 method get result. So, and by default, it's an array, as you can see. So, and now the names are included. For example, the feature name, spill length, because I trained a neural net on the Penguin dataset, and the class label. But it's also possible to get the result as a data frame where we have the points and the feature, the class label, and the value. Last step, our third step, where we can visualize the results by calling simple R generic functions. So you can plot individual results where you can adjust for the output class or the data point. For example, in this case, we created a visualization of the data point 42 for the class Adelie. This is the default class. So by default, we use the first given class label. And it outputs an ggplot object, so you can add custom modifications like the theme, or if you want to add some custom facets, whatever you want, you can add some modifications. And it's also possible to summarize the results of the whole data set or a subset of the data set in box plots. In doing so, you can add a process function that is applied to all the results before we create the box plots. For example, in this case, we only created the box plot of the data points corresponding to the type Adelie of the Penguin, and we don't use any kind of preprocess function. And yeah, so we created some nice box plots for the data, and we can see, for example, the bill length has a high positive impact to the output for the Adelie class. Now here's a more extensive and complete example where I use the VGG19 pre-trained model in Keras on the ImageNet dataset. So first of all, I get the model, then I load the image, do some pre-processing, and after that, now we come to our 3 steps. So in the first step, we create our converter. It's very simple, so we only pass our model. Then in the second step, we apply the LRP method with alpha beta rule. Alpha is equal to 2 and beta is and we only calculated for the output class 8 because 8 corresponds to the rooster, and spoiler, the image is a rooster. And then we need to set the channels or the data format of the input, and Keras provides it as a channels last. So the argument channels first need to be forced. Then we pass our rule. And there's another special thing for the ImageNet dataset because they are flipped according to the y-axis. So we need to flip it on the y-axis, and then we plot the result. And as a result, this one is the result. So we have our original image data, the rooster, and this is the result for the LRP function. As you can see here, we have the shape of the. So as a conclusion and an outlook, so Insight is a very flexible package, easy to use, and has good visualization tools. And everything is in one package. So it provides the most popular methods like gradient times input, LRP, deeplib with all the rules. It's a deep learning library agnostic package, so you do not need for another package for each model where you trained it in. And it's the first and only R package for feature attribution methods for neural networks. And as a short outlook, we are currently working on non-sequential model architectures. So for example, you have multiple input layers or some special layers like residual. We also are currently working on a fast implementation and GPU calculations, which so we need to adjust it. And in the long term, we want to implement other methods like deep lift SHAP, which is a combination of SHAP and deep lift, and a composite rule for the LRP method. And in addition, we also want to extend for categorical features. Then I would say thank you for your attention, and please check out our package. And if you have any question or contact me, here is my contact, and try it out. Thank you for your attention.
Thank you very much, Niklas. I think it was a really great talk. And yeah, seems to be a great package. So let me see if we've got.
I hope so.
Yay! Let me see if we've got questions in the chat. So there's no question for the moment, but let me ask you one question. So you talked about interactive plots, and you said that they could be created. Can you expand a bit on this? Like, how does it work, and like, would you have an example of it?
So it's implemented in the plot function, so in both in boxplot and plot. So you can add the argument as plotly is equal to true, and then you can create the interactive plot with plotly. And one result I prepared is, for example, this one from the same image. You have all the relevant information, so you can see the relevance, the data point, the output class, the height and width, and you can also zoom in and look in more into detail and whatever you want. Yeah, and as I said, it's also you can also plot multiple inputs and multiple classes, but this is only for one class and one output. So it's also possible to utilize multiple inputs or instances at once.
Very cool. Yep. Thank you. And just like when we use interactive plots, now the challenge is how to be able to transfer these interactive plots when you present to senior stakeholders, for example, because obviously, at the end of the day, so we can play as data scientists, as statisticians, we can play with the interactive plots, but then the question is, how do you make this a PowerPoint, or how do you make this a Word document and still not lose the interactivity? But yeah, I think they're great.
Yeah, that's a big problem, I would say. For me, it was quite difficult. I tried to add this HTML file in my slides, but somehow my Ubuntu visualizer doesn't. So I was not able to implement it in such that it worked.
Yeah. But yeah, if anyone in the session has a good idea on embedding this, please feel free to share in the chat. So for the sake of time, I see that there's another question in the chat. So I'll let you have a look at it, Niklas, and answer in the chat, so that we don't run over time. So thank you very much, Niklas. It was a great presentation.
Thank you very much.
Yeah, thank you, and good luck for the remainder of your PhD.
Yeah, thank you very much.
Welcome. So our last speaker today is Marvin Wright, actually from the same group as Niklas. So you might know Marvin from his package, because he's the author of the random forest package called Ranger. He's the head of a research group on interpretable machine learning in epidemiology at BIPS in Bremen. And he's a professor at universities of Bremen, Germany, and Copenhagen, Denmark. So today, Marvin is going to be talking about testing conditional independence in supervised learning algorithms with the CPI package. Marvin, the floor is yours.
Yes, thank you very much. So I have to select the correct window. Here we go. So welcome to my talk on testing conditional independence in supervised learning algorithm with the CPI package. So, and first I'd like to thank my co-authors, Christine and David. And we'll be talking about conditional variable importance. So remember Niklas had on the first slide this classification into model agnostic and so on. And he was talking about a model specific method. So we're now still talking about post hoc methods, but this is then the model agnostic method. We'll talk a little bit about the global and local. We'll talk a little bit. And we add a further dimension because now we have conditional variable importance. And I'll explain what that is. So let's start with the typical confounding example. So in epidemiology, you would have an exposure and an outcome, and you're interested in effects or associations between the exposure and the outcome, but there might be confounders. So one example would be you are interested in the effect of drinking coffee on getting lung cancer. And in fact, there's a confounder, smoking. So people who smoke more often drink coffee. And there is an effect, obviously, of smoking on lung cancer, but there's no effect of coffee on lung cancer. And the typical confounding problem here is you don't measure. If you don't measure and for smoking, you will find an association between coffee and lung cancer, which is obviously wrong, or at least we don't know of any association between the two. And a more easy example would be if you have sunny weather outside, people buy more ice cream and people get more sunburns. But there's no effect I know of ice sunburns, but there's only the confounder association, or only the confounding variable causing both of them. And if you now use a machine learning method of your choice and calculate, for example, permutation feature importance, but it also is the same for several other methods, you will find an effect of your confounder, Z, but you'll, so the one on the right, I think you can see my mouse, and you will also find an effect of X. So in this case, you will find an association between buying ice cream and getting a sunburn, which is obviously wrong. So, and that's because this is a marginal measure. What we are going to do in this talk is develop a conditional measure, which then gives an effect to the confounder, but doesn't give any effect or association to the exposure, or in this nice example, the ice cream. And I would say to this question, this is the correct answer. So a marginal measure is used to understand the prediction model. So is a variable important for the model, and which effect does a variable have on the model's prediction? So statistically speaking, that means you test against the null hypothesis of your variable of interest xj being independent of your outcome y, and you don't care for your other variables of the other x's. And the conditional test is used to understand the data, then still using a prediction model here. And here the question is a variable associated to the outcome, and which effect does a variable have on the outcome? And the difference here is that the null hypothesis is your variable of interest xj independent of y, conditioning on all the other x's, including potential confounders. And this is our method. It's quite simple. And if you know importance, you will find that it's very similar. And it goes by fitting your model to original data. You calculate your loss, for example, mean squared error. And we'll see later you have to use some cross-validation, holdout, or whatever for that. And then you replace your variable of interest by its knockoff version xj tilde. So I'll explain at least a little bit what that is later, and determine the loss after the knockoff. And then your conditional predictive impact is just the difference of the two losses. So the only difference to permutation feature importance is in this step of the knockoff. So in permutation feature importance, you permute a variable, and here we replace it by its knockoff. And that's exactly the reason why it is a conditional measure, because the knockoff results in our xj tilde, so our knocked off version of the variable of interest is independent of y, but it preserves any correlations between the x's. And yeah, by that, it is a conditional method. And for knockoffs, there are many methods, as we will see, but the general idea is for a knockoff construction that given your feature matrix X and your outcome Y, you construct the knockoff matrix X tilde, which has the same correlations as the original X, and there's even the same correlations here, the third row here, between the xj in the original data and the xk in the knocked off data. But most importantly, your knockoff matrix is independent of your outcome conditioning on X. So, which is obviously not the true for your original, not the truth for your original data X. And many methods have been proposed. I won't go into details. There are multivariate Gaussian sampling, hidden Markov models, generative neural networks, and so on and so on. And the CPI just works with any of those. So we just need a proper knockoff for our method to work. And we'll see later that we can use different ones. A big advantage is that we have statistical inference without any permutations. So we can, we have shown in our paper that the CPI estimate is asymptotically normally distributed. So we can just use the instance-wise loss for statistical inference. So that gives a little change to our algorithm. And that means we do the instance-wise loss, overall loss. So for example, instead of the mean squared error, we just take the squared error. And then we do all the steps with the instance-wise loss that gives us a delta vector instead of just a CPI estimate. The CPI estimate then is the same because you do then the mean of the instance-wise loss, which is the same as doing the mean in the very beginning, at least for the mean squared error. And then we can get p-values and confidence intervals based on that delta vector. And then we can simply use paired t-test or Fisher's exact randomization test for statistical inference. So we have shown in our paper that we control type 1 error and achieve power except for misspecification. So here on the right, we have nonlinear data and a linear model that obviously cannot work. And for zero effect sizes, we are always at the nominal 0.05 level and reach a high power, depending a little bit on the model and the data generating process. And we have also shown that we have quite competitive performance to other methods that do conditional variable importance. You might argue that here the blue one, the GCM, outperforms our method, which is red on the linear data. But then if you look at the blue one, the dark blue one here on the nonlinear data, it completely fails. And obviously in reality, you usually don't have strict linear data. So then let's come to our package. So our package is based on the MLR3 framework. So first we have to load MLR3 and MLR3 learners and then our package CPI. And then we just call the function CPI, give it a task. So an MLR3 task, a learner, and a resampling strategy. If you know MLR3, then this will be very easy for you. But even if you don't, just using the examples, I think it's not super difficult. So we just use an MTCast task, which is integrated in MLR3, a linear model as a learner for a regression task, and a 3-fold cross-validation in this example. And that gives us, for each variable, it gives us a CPI estimate, the standard error. These are quite big because the data is very small, and test results. And we can easily, that's nice about MLR3, we can just replace our linear model by a random forest, just changing one line. Or we could go from cross-validation to holdout. Or if we use a random forest anyway, we could use out-of-back error estimation that saves us some runtime. Or we could also do classification. So now let's take the wine data set out of MLR3, which is a classification problem. And now we just have to be careful to select the classif.ranger instead of here in the regression case where it's a regression ranger. Or we could change the loss function. So for example, for classification, the default is log loss, but we can also change it to classification error, and the CPI method still works. We can also do categorical features. So let's take the Boston housing data. This is also an example on how to use your own data set. You just use as-task regression in your data set. And then again, a regression problem and holdout, but that will give you an error. And that's Gaussian knockoffs cannot handle factor features. Consider using sequential knockoffs. Okay, then let's use sequential knockoffs, and then it works. So the reason is the default is Gaussian knockoffs, and Gaussian knockoffs only work with numerical data. So these are quite robust to normally distributed data, but they won't work at all for categorical data. But you can easily change the function to generate the knockoffs, and the sequential knockoffs from the sig knockoff package, for example, they work on categorical data. So we can also do some plotting, but we don't have such nice plotting capabilities as the Niklas package yet. But it's also not super difficult here to create, for example, a bar chart with error bars. And as an application example, I'd like to show you one from a genome-wide association study. So that was a huge study on childhood obesity with children from 7 European countries, and the target was so it is a regression task, and we are interested in body mass index. So if you have a high body mass index, you're likely to be obese if it's quite high. And the data consists of SNPs, so single nucleotide polymorphisms, that are genetic variants, and we have 300,000 of them. But we are often interested in the effects of genes, and one gene consists of many SNPs. So we want to do some grouping. So the research question here is which genes are associated to high BMI. So we want to find genetic variants that, if we want to formulate it in a causal way, which cause obesity. And we can do global estimates. So here we find these are then the grouped variables. So the data is actually SNPs, but we get effect estimates for the variable importance for whole genes. And we see here that we find this genes always have these funny names, that we find this R3HDM1, but quite a high effect. And the FTO, which is interesting because this is well known to be associated to obesity. But we can also do subgroup estimates without doing any subgroup analysis. So we just get values for each person or any instance or observation in the dataset, in this case, for each child. And then we can just plot the CPI values by subgroups. And here we find this, for example, the two first ones are mostly predominant in males, but not so much in females. And the third one here, for example, is actually quite high for males, but exactly at 0 for females. So that's seems to be very different. And we can even do local estimates. So we get, so each of these panels is now one child. So the first one is an 11-year-old boy from Hungary. And for that boy, it seems like the R3HDM1 has a huge effect. And for the second one, which is a 10-year-old girl from Sweden, it seems like FTO is important. So that seems to be very different for different children. But we don't get any error estimates or confidence intervals for the local estimates. So we have to be a little bit careful about this. So to sum up, we have a model agnostic method. So that works for all model classes. We are also knockoff agnostic. So we just accept all kinds of knockoffs. That's a conditional method. So we can adjust for confounders and handle correlations. We can do statistical testing without permutation tests or bootstraps. And we get global, subgroup, and local interpretations, and we can do feature grouping. And so far, successful applications were on just numeric data. For example, gene expression data, we used Gaussian knockoffs for that. And on mixed tabular data with sequential knockoffs, and also that last example on genome-wide data, here we used hidden Markov knockoff and the group CPI. What we still have to do is to do some more simulations and benchmarking on mixed data. So we did quite some benchmarking with the Gaussian knockoffs, but not so much with the sequential knockoffs. We would like to look into some applications in causal discovery because they use conditional independence tests all the time. And we'd like to add some visualization tools. So here's the link on our paper, and the package is on CRAN and on GitHub, so feel free to use it and create issues or pull requests if you have any questions or suggestions. Yes, thank you very much. Now I'm open for questions.
Thank you very much, Marvin, for another great talk. It was good to have you back to back with Niklas. Pretty nice to have you both in the same session. So there are some questions in the chat. So the first question is, do you have any plans to adopt CPI to work in tidy models workflow?
We don't have any plans, but we thought about it. It shouldn't be super hard. So what we need is, let me go back to the slide with the example. So important is we need some kind of resampling, and that's obviously possible with tidy models. And we need then access to the models fitted on the cross-validation forts. I guess that's also there, but I haven't looked into it. So I think it's possible. We also thought about putting it into Python, for example, with sklearn. That should also be possible in the same way. But we had a first version with MLR, and now I adapted it to MLR3. That was a little bit harder than expected, but not super hard. But the others should also be possible.
Okay.
And we are very much open to any pull requests if anyone is totally into tidy models and would like to help.
Yeah. Cool. Then we've got another question, which is conditional independence can be problematic if you've got closely related regressors. If you consider the sunburn example, where you might have daily maximum temperature and daily average temperature. So do you have a recommendation how to deal with such closely related groups of regressors? And are there dedicated knockoff methods?
So that's a good point, a very good point, because the problem is you get, with the conditional measure, you get the additional effect of a feature taking into account all others. And if you have two which are almost the same, which have a very high correlation, then they will both get a low value. Because having the other, they are not very important. And that's, I'm a little bit, I maybe should stress it even more, that I said in the beginning that the conditional method is the right, so give the correct answer here on that ice cream example, which I think it is true, but conditional is not just better. There are many cases, many problems. So one is that problem. I don't really have a solution for that. And another one is often you're just not interested in what are the effects in the data, but you just want to interpret your model. So in this example, if your machine learning model uses ice cream to predict sunburns, that's fine for prediction. And you might want to know. And if you want to know that, you should use the marginal method and not the conditional one. So it completely depends on the application. Yeah, but for the problem of two closely correlated ones, I don't really have a solution. That was the question about the symbol. Yes, and Achim already answered.
So yeah, and I can see there's another question in the Q&A. I'll let you have a look at it. So
should I answer it now or should I?
Yeah, I mean the question. Yeah, we've got a few minutes left. So the question is, can you please clarify again why conditional importance values are important even for non-causal models like neural network?
So the obviously causality is the next step you want to do if you're interested in really understanding the data. But take my example with the genetic data. And let's say in that example, I used the random forest, but you could also use a neural network. So if you find a way to fit that high dimensional data in your neural network, why not? And then you might still be interested in what is the association of a gene and a disease. So you don't have to do causal modeling to be interested in associations. So in general, so if you do the marginal one, then you're interested in understanding your model. The next step would be to go for associations. That's not causal yet. That's what we do with conditional variable importance. And the next step would be to do a causal analysis. If you want to know if here in this example, from X to Y, if these two are only associated or if X causes Y. And yeah, we have some ideas how we could use our method for causal discovery, but we haven't really done it yet.
Cool. Yeah, thank you very much, Marvin, for your great presentation. So we're almost at the top of the hour. So I want to thank Igor and Bernardo. I want to thank Niklas, and I want to thank Marvin for this great session, for their great presentations. I think we all learned a lot. So yeah, thank you for being part of it. Thanks to the audience for the great questions in the chat. And as the speaker said, you know where to find them. You can find them on LinkedIn. You can find them, in the contact info that they mentioned. So yeah, thank you very much. It was a great session. I was very happy to be part of it. Up next, we've got a keynote from Amanda Cox in just over 30 minutes. It sounds very exciting. So stick around and go join the keynote session. Have a nice remainder of the day and talk to you soon. Take care. Bye-bye.
Thank you.
Thank you, Guillaume, for leading this session.
Thank you. Bye.
Yeah, welcome.
Bye.
Bye-bye.